Hello, and welcome to another creative coding video. This is the first in a series of videos looking at ray tracing. Now, ray tracing comes from the really old kind of idea of trying to create images in a computer that are in some way realistic. Many people have been trying to do that using all kinds of techniques, and ray tracing is a technique that sort of borrows ideas from the laws of nature, physics, the way light works, and it can create some really stunning effects. It's quite intense in terms of computer power needed, but actually today in 2020 most of the computers we use can create really good results just using the code that we write. Now, because it's quite a large topic, ray tracing, you can buy massive kind of textbooks on it. We won't cover everything. What we'll do is just look at a few of the basics so that we have really got the core idea and then extended it in a few interesting and fun ways over the course of maybe 3, maybe 4 videos. So we won't make a very, very long video. We'll chop it up and we'll make some progress today, and then in the next video we'll do a little bit more, and so on. What we're looking at here is an image that we should be able to create sort of halfway through this sort of set of tutorials, and what you can see are spheres that appear to be lit by a light, and we can see that the lighting looks kind of okay-ish. There's an area where there's lots of light and there's some shadow. In fact, there's a hard shadow here cast by these two balls. We can see reflections, which is quite a sophisticated idea actually, being able to see reflections of other objects in other objects. So we'll definitely be covering that. And here's another example towards the end where we'll be able to not just have colour, but objects with texture. And if you've been following these video tutorials, we'll have covered a really interesting method called Perlin noise, and it's really useful for creating textures, and actually that's what we've used here. But let's look at other people's examples of ray tracing. So what we're looking at here is almost the classic 1980s, 1990s ray traced image. Back in the day, computers are not as fast as today, and it was quite impressive to get a computer just to produce something like this, a silvery metallic ball reflecting a checkered landscape in its surface, being able to see shadows and being able to see some kind of light, like a specular highlight, where the light's coming directly onto the object. And that was impressive. I mean, these things took hours to calculate and draw, but that was the state of the art in those days. And many of us were really excited by seeing these things and trying to create them ourselves. Now, this image may look like a photograph, but it's not. It's created using this magical technique called ray tracing. It's a little bit more sophisticated than the one we've just been looking at, and you can see there's all kinds of interesting physical effects taken into account. There's blurriness, there's sort of a focus area, like a depth of focus. There's a very realistic sort of highlight there from the light. There's a kind of a matte, half shiny, half matte surface. There's some really interesting shadows that are hard and soft. You can see reflections. Overall, if I'd have told you this was a photo, you probably would have believed it. I mean, I'm quite surprised it's computer generated, but that's the power of ray tracing. We'll talk about what it is, but I'm just showing you some examples to get you motivated. And here's another one which really shocked me. These glasses, this is not a photograph. These glasses are entirely modelled mathematically. They exist only as mathematical descriptions in terms of curves and circles and so on. The objects' materials are modelled, so light is bouncing off them, transmitting through them, refracting a little bit, diffracting perhaps. It's extremely realistic, and this is closer to the state of the art. Actually, this is a few years old. I should say the images we've just been looking at come from a website called Povray. Now, Povray was one of the early ray tracers 20 sort of years ago. It's still going today. It's open source, and it was very sophisticated, and it allowed lots of people to have a go themselves because it was free. I definitely recommend having a look at the software. It's much more advanced than what we'll code ourselves, and if you can find resources like textbooks or guides on how the internals work, it's really kind of interesting to see how the professionals do it. So credit to the original people who created this, and I'll kind of create a link in the description so you can see the original images. But that's really why we're excited by ray tracing. It models light moving around a scene in a way that is as best as we can understand how nature works, how physics works, and we're trying to model that in a computer. And this one I had to include, another one from the Povray website. That's amazing, isn't it? I mean, it looks so realistic, like a photo of pebbles on a beach, but it's not. This is entirely computer generated. All these pebbles are modeled mathematically, and I think the key with this image is the textures. They really kind of make you believe it's real. I think it's fantastic. So these are just examples of state of the art, what people can do. But we're just going to look at some of the basics today. Great. So we're going to take it in steps. We're going to think a little bit about objects. In fact, we're going to pick a very simple object, a sphere to start with. And we're going to think about how we see a sphere, when we use our eyes to look at a scene. And then perhaps not today, in the next video, we'll think about how we colour the sphere, because we're going to have to draw an image using pixels. We're going to have to decide how to colour those pixels to make sure that the rendered sphere in some sense has shadows in the right place and highlights in the right place. So that's what we'll kind of get to. So let's jump right in. Let's think about a scene. Let's break it down into the various kind of things that are working. So here we're looking at a scene, and we have an object which we've chosen as a sphere. It could have been a tube, it could have been a cube, it could have been a pyramid, it could have been a flat surface, but we're using a sphere for now. We have a light source because without light we can't see anything. We are only able to see things because light is moving from this light source to an object and ending up in our eye. It could be an eye, it could be a camera, but something is doing the seeing. We also have this idea of a viewport, because if we're going to use a computer to model this scene, we have to pick some kind of rectangular shape like a window or a viewport or a canvas to draw pixels on, and that rectangle will match, I guess, what we draw on our screen. It also limits what we can see, because we're not going to try and see everything. When we use our own eyes, we don't see all around us. Our field of view is limited. So let's think a little bit more about the mechanics of what's happening in this scene. So here is the light source, which could be the sun, it could be a light bulb, it could be the moon, it could be something else. It is emitting light, and we can think of them as light rays, straight lines emitting out of the light source and entering the scene. Now this one that we've drawn misses the object. Because it misses the object, it doesn't interact with it in any way, and more importantly, it doesn't return to our eye, so it might as well not be there. It is there, but it doesn't reveal anything in the scene because it's missed everything. This one does hit an object, but the light bounces away. So yes, it does interact with an object, it hits an object, but because it bounces away from us, we again don't see the object because of, due to that light. If all the light was being bounced away, we wouldn't see the object. And in this example, the light is hitting the object and it is being bounced right into our eye, into our camera. And that is how we see the object. It is the three things. Number one, a light source emitting light. Number two, some of that light hitting an object. And number three, some of the light that hits the object actually reaching our eye, because it could bounce and just miss our eye, which means it's not useful for us. So that's how we see an object, and that's, I guess, what we're going to have to model in some sense. That's what simple physics is telling us is happening, and we should be able to do that. We should be able to model kind of mathematically rays emerging from a light source, traveling through a scene, hitting an object, bouncing, and going into our eye. That's what we're going to be doing. But actually, what we've just described is mathematically sensible, I guess. It makes sense. It's not incorrect, it's mathematically correct, but it's inefficient. What do we mean by that? Well, if you think about this light source, it's emitting light rays in all kinds of directions, and we'd have to model them all, because we don't know which ones will hit the object. So we'll have to shoot light rays in all kinds of directions and hope that some of them hit the object, or more than one object if we are modelling more than one object. And then we have to try our luck again and hope that some of the ones that did hit the object also go into our eye. So you can see we're going to have to run lots and lots of rays, do lots and lots of calculations, and they are fairly intensive calculations, lots and lots of calculations, in the hope that some of them hit the object and then some of those hit our eye. That's not very efficient. Let's see if we can make this more efficient in a different way. Let's see if we can think about the problem differently. And the way to think about it is to reverse it, because we know we are only interested in light rays that hit our eye. So we can actually reverse the directions. We can say, let's start with the light rays at our eye, let's shoot them into the scene, and some of them will and some of them won't hit an object, and then some of them will and some of them won't go back to the light source. So we're reversing what we're doing, but we're cutting out a lot of unnecessary work by doing this. It's not perfect by any means. I mean, some of the light rays will hit the object and bounce away, not towards the light source, which means that they were wasted in some sense because they weren't real light rays. They were never going to come from the light source and hit our eye. Some will just miss the object entirely, another wasted ray, but a few will hit the object and go back to the light source, and that's probably as efficient as we can do it without using really sophisticated techniques, which we won't go into today, because we just want to focus on the core idea. There's one that doesn't go back to the light source. But actually, this is an interesting point. This one here that does go back to the light source, how would we colour that? This is a red sphere, and maybe that's yellow or white light. How would we colour that pixel that corresponds to the light bouncing just here compared to one here? Because this one, the light bounces in some other direction and doesn't go anywhere near the light source. Intuitively, this should be dark or darker because it's not illuminated by the light source, whereas this one is going directly back to the light source, which suggests it should be lighter in some sense. It's seeing a lot more direct light. So that's a useful kind of intuition to think about and carry with us as we go forward, because that idea will be useful. And this picture really just shows what we're doing with this viewport, this window. It'll be a rectangle which we divide into pixels, and those pixels are the ones that we're going to be using when we draw using our code. And we test pixels. I mean, in fact, we won't just test them randomly. We'll go along methodically, along the rows and down the columns, and every pixel will shoot a light ray from our eye to that pixel, continue it into the scene, and see if it hit an object or not, and see, you know, whether it went towards the light or not. That's what we'll do. So the logic of our code will be work through all the pixels in this viewport and test whether the ray going through them hits an object, and then decide how we colour it. Today we're not going to decide how we're going to colour it, that's in the next video, but today we're going to just focus on, did we hit a sphere, an object, a sphere or not. That will require a little bit of work, and then subsequent tutorials will have a lot less to do because we'll have done a lot of the work already. Great, so let's well, I was going to say let's code, but actually we need to just think a little bit more about how we do that testing mathematically. So before we dive into looking at algebra, and there isn't a lot, let's first talk in plain English what we're trying to do before we look at the algebra. And I promise the algebra may look scary, but it's nothing more than what, you know, we would have done in secondary school. Very simple mathematics, really. You might have to kind of shake your brain to remember it, but it's nothing advanced at all. So in plain English, the idea is we're going to shoot a light ray from our eye into the scene, and we're going to test in some way whether the light ray hits the object or doesn't. That's it. Today, that's all we're going to do. So we need to think about a mathematical description for both the light ray and the sphere. So let's draw some pictures to help us think about this. So a light ray will have a starting point where the camera is, or the eye, we call it camera, and it will have a direction and it will carry on in that direction. And we can call that direction, which is a vector because vectors have direction, we can call that D for direction. You can name it anything you like, but keep it consistent. By convention, we'll have that direction vector with a size, a length of 1, a magnitude of 1. This camera position doesn't have to be the origin, so we might have the origin in our world here. So the vector to the camera or the eye is C, and the ray will extend in this direction. And if we called the ray R, up to a point, say there, that means the ray equals the starting point C plus, just write that, plus some kind of factor, let's call it T for time, times the direction. So we start at C, we start there, and at time 0 we stay there. As time increases, we increasingly move in this direction. So this is the mathematical description for that ray. The ray vector is the camera vector plus t times the direction. We could have used another letter for that parameter, but t makes sense because it reminds us of time. Let's now think about how we mathematically describe a sphere. And a sphere is like a circle, so we'll talk a little bit about a circle first because the ideas are the same. Let's draw another picture again. So let's say we've got a center, so we have to define where the middle of a circle is, and we're drawing a circle here. Not drawing it very well. That's a circle. So the center so there's the origin of our world. So the center is at vector S. That's the sphere center or the circle center. Now, to define a circle, we take advantage of the fact that every point there is at the same distance from the center. So that's R, the radius. So every point on the sphere or on the circle, in fact the same for a sphere, every point on the sphere is the distance r radius from the center. That is a definition of a circle and sphere. So how do we say that? Well, we can say if there's a point P that's anywhere on the circle, so we can say P minus S, the magnitude of that means the magnitude, the length of that vector, is R. Why did we say P minus S? Let me pick a different color just to show us. So we're interested in this vector from the center to a point. This thing is P minus S. So if we had S, which is going backwards, minus S, plus P, if we add the vectors together, we get this one here. I'll colour that in a green just to show us there. So P minus S is from here to here, that one there. So it's saying the length of that, wherever P is R. That's the definition of a circle or a sphere. So we've talked about how we define a ray. We've talked about how we define a circle or a sphere. And this picture just brings those things together. So we said a ray is C plus TD. So that's the direction here, starting at the camera and moving along the direction. And as t grows, the ray kind of extends further. And we are wanting to test whether this ray hits the sphere. Here is the picture showing what we just talked about, the definition of the circle and sphere, where we said r minus s, or p minus s, squared is radius squared. It's simply saying that this distance here is r always. So how do we test whether two mathematical objects intersect? Well, if you remember going back to sort of school days where we had very simple algebra, we might have had something like, I don't know, y equals 2x, and that might have been something like that sort of line, and we might have had y equals, I don't know, 5, which was this sort of line, and we wanted to see where the crossing point was. What we would do is we'd equate these two things, we'd put them together, and we know if they cross, if they touch, we know that either x is the same and y is the same. And here we can do that, we can say y here is this y, that's 5, so that means we can say 2x equals 5, therefore x equals 2.5. And that's where that intersection happens. So the point we're trying to get across is that we equate the two definitions. We bring them together and say they are sharing the same variables. If we had more complicated curves and lines, we would still do that. We'd say something like y equals blah blah blah, and another one might be y equals blah blah blah, something different. All we'd have to do is equate them, work out the algebra, and if they did kind of intersect, then that would fall out. And sometimes that doesn't happen. So if we say we've got I don't know, let me clear the screen to show us better. Let's say we've got something like y equals x squared plus 2, and another one saying y equals 1. Now, do these two curves or lines intersect? Well, let's just draw a rough sketch. So y equals x squared plus 2 would look something like this, and there's a distance of 2 here, so it doesn't touch the x-axis, and y equals 1 goes like this, so they don't touch. There's always a gap between them. And if we put them together, we'd say x squared plus 2 equals 1. Or we could say x squared plus 1 equals 0. And if we try and solve that, x squared equals minus 1. So x squared equals minus 1. That doesn't have a normal answer. You know, something squared is always positive. So we don't have any ordinary. We do have special answers to this if you know about that. but you know, normal mathematics, there's no answer to this, and that makes sense because the two lines don't cross, and that's useful to us. I'm not covering this because it's fun. It is fun, but this idea when things don't intersect is useful for us because we'll see things like this. Great. Let's go back to our kind of logic of how we do this testing. So we're going to make those two expressions the same. So on the left hand side we've got r minus s squared is the ray. Yeah, let me go back. So we're saying the ray, so we're saying before we had p minus s squared is r squared for any point on the circle, but we want those points to be the ray, so we're locking it down to potential here and here as the crossing points. So let's write that out. Not just p, but the ray minus s squared is r squared. So that's saying that the ray is a distance radius from the centre of the sphere. That's what we're asserting. Now the ray we know is c plus td. That's how we describe the ray. So we brought the two shapes together, the two kind of objects. And we can expand this out in the same way that we do, you know, expanding out sort of something plus something squared or something minus something squared. If you remember something like a plus b squared, at school we said we could do a squared plus b squared. You could work it out yourself. A squared plus b squared plus 2ab. And if it was a minus b squared, that was a squared plus b squared minus 2ab. You could expand it out manually and do all the combinations and tidy it up to get these answers, but many people will have memorized these because they were drummed into us at school. So that's what we're doing here. We're expanding out this thing squared, so we've got the first one squared plus the second term squared minus 2 times the first times the second. So this is just a squared plus b squared minus 2ab. So nothing, you know, advanced here at all so far. So that took us up to here. Now here we've got another squared thing here, this kind of expression. We can expand that out again using the same a plus b squared. So this will become c squared plus t squared d squared plus 2tcd. That expression there, this one here, is this one here, and all the rest of it is what we had before. Now that looks like a bit of a mess, doesn't it? I'm not going to lie. But what we can do is we can spot t and kind of collect the different kinds of t. So we've got a t squared, we've got a t, and then we've got something that has no t in it. So we're solving for t, solving for time, because we want to know whether at any time that ray does hit the sphere. So if we did kind of expand this out and collect those kind of t squareds and t's and not t's, we'd end up with d squareds here, we'd end up with this expression here, and this long thing here. And actually you can spot here that we can re-simplify this down now, because that squared plus that squared minus 2 times first times second, that's simply this thing here. That's almost undoing the expanding. Just to tidy it up, there's nothing particularly special there. So this thing we've got here, although it looks horrible, is actually quadratic in T. It's just like saying, you know, ax squared plus bx plus c equals 0, a quadratic equation. And we did loads of those at school. So we know how to solve these. Let's remind ourselves. So in general, if we have something like a x squared plus b x plus c equals 0, that's a quadratic equation. And a could be anything, b could be anything, c could be anything. If a is 0, then this is really simple. And at school we did lots of these and practiced it. We could use factorization, we could use other ideas, but eventually we came across a kind of a general formula, and it was something like, if I can remember myself now, what was it? Minus b plus or minus the square root of b squared minus 4ac all over 2a. That's what x equals. Phew, now that's the general formula for solving quadratics. And you'll notice there's a plus minus here, which means we get two answers for x potentially. Why is that? Because a quadratic can hit a line twice potentially. It can hit it never. It can hit a line just once, or two answers that are the same, or it can be hitting it twice. So that's what that accounts for. And these a's and b's are these things here, a, b and c. And this thing here, this square root, is quite important, because if the thing inside it is negative, the square root of negative, we've kind of already said that's a funny thing. So that's this case here where we don't have an answer, they don't cross. So that's when, let's call this thing a determinant, like a delta, this Greek symbol. If that is delta, let me choose a different color. We're saying delta is less than 0. There's no answer. There's no cross, they don't intersect. Here delta is more than 0, we get two different answers. And here, if delta is 0, we get one answer, and some mathematicians say it's two answers that happen to be the same. So that's important. So let's apply that to this quadratic equation. Instead of x, we've got t. That's just that expression again that we were looking at, ax squared plus bx plus c, and that's the general answer. So in this case, a is this thing here, b is this thing, and c is all this thing. And that's that discriminant we talked about, the little bit, b squared minus 4ac. So this discriminant is that thing there. B squared minus 4ac, just going to multiply that out. So b is this thing here, so we've squared that, minus 4 times a, which is that, times c, which is all that. Got an extra bracket there, that shouldn't be there, should it? Oh well, spotted a mistake. Great, so illustrating in terms of our scene again, if we shoot a light ray out, if that determinant is less than 0, it doesn't touch the sphere. If that determinant is 0 or more than 0, it does touch the sphere. That's the heart of our test. That's the core of ray tracing. Everything else is some fancy extension, some refinement, some cool new idea. But the very core of ray tracing is this, the idea of sending out rays and testing mathematically whether they hit an object or not, using the mathematical definitions and solving them. And for lines and spheres, we can use that determinant. And remember, this determinant is just this thing here. It's made up of the direction of the ray, the camera position, the sphere position, and the radius of the sphere. And it's using those in this expression for delta, the determinant. And that's what we'll need when we code. So before we dive into coding, let's kind of write out in kind of pseudocode, in English as it were, what our code might be doing. So for every pixel that we're testing on our canvas, on our viewport, we want to work out the ray direction from our eye, because depending on which pixel we're interested in, the ray direction will be different. So we need to work that out first. That gives us the D vector, the direction. Then we need to say, does it intersect the sphere? And we use that quadratic determinant. And we know that in order to calculate that, we already have the position of the sphere, the radius of the sphere. If it does intersect, if the answer is yes, and if the determinant is more than or equal to 0, we set the pixel color to the color of the sphere. Now later we'll make it more sophisticated. We'll think about shadows and highlights and other things. But today this is as far as we're going to go. Like I said, this is the core. Everything else is building around this core. If it doesn't intersect, we can just color it a background color, because the ray has missed the objects and gone into the distance, and perhaps we're seeing the sky. We don't even have to do this bit, we can just leave it and ignore it, leave it black, but it'd be nice to kind of color it some kind of sky color. So let's have a go. I'm logged into Open Processing as usual. I'm setting up my simple setup function, and I made sure that the simple library is enabled. And I'm starting with an empty draw function. So let's set out with some basics. We can kind of think aloud as we do it. I'll just increase the text size so it's easier to see the text. There. Great. So the first thing we want to do is define where the camera is. We're just setting out, defining the scene a little bit. So the camera. So var camera location. Now, how do we define where the camera is? Well, we need 3 coordinates, x, y, and z. Let's think a little bit about our scene, our 3D scene, before we do that. So imagine we have a 3D scene, and we have our camera or eye looking into the scene. We've got a rectangular viewport which we're looking through, and it's made up of pixels like that, and behind that window we've got an object like a sphere, just kind of colouring it like that to give it a sense of 3D-ness, as it were. So we could define our world as x, y, and this is the conventional use of x and y. I know that in Open Processing and P5.js the origin's at the top left, but that's not how many other kind of situations have x and y. They have x and y starting the bottom left, and we'll have z going into the distance, z like that. So x would be along the viewport, y would be up the viewport, and then into the viewport, into the scene, would be z. So we could be kind of centered like this, like that, and we could be at 0, 0, and then say minus, I don't know, minus 100. So we're standing back from the viewport by a distance of 100. We're backwards from the viewport. Into the viewport, the sphere might be at, I don't know, 0. It could be 0, and it could be 20. So the distance into the scene is 20. So that's 20. So the center of the sphere could be there, 0, 0, 20. And we can give it a radius of, I don't know, 10, 5. We'll try a few ideas. We will have to think a little bit about how big that viewport is. We could give it, I don't know, a width of, I don't know, width and height of say 20 or something. Can do that. So the camera location, we can fill in some numbers now. We can say it's at x0, y0 and minus 100. But in JavaScript, which is the language we're using, we don't have vectors like that. We can't just say brackets and then vector. We could have a list, I suppose. We could have something like that. So it's a list. But then we would have to manually do calculations like multiplying and so on. Some languages very helpfully provide an ability to work with vectors and matrices, and provide functions for doing things like multiplications and so on, working out magnitudes, that sort of thing, dot products. JavaScript on its own doesn't, but P5, which is kind of the extension that we're using, does have something called a P5 vector. It does the job. It's not quite as elegant to use, I'd say. You'll see why later. It just requires more typing than really necessary, but it works, so we'll use that. So we're going to use create vector. That's the magic function for creating vectors, and that creates essentially a list really with 3 things in it, and then lots of convenience functions around that. Great, so define where the camera is. Let's define the viewport. We can say var viewport location, so the middle, the center of the viewport will be at 0, 0, 0, and we have to give it a width, so viewport width equals, I'd say 20. We can always adjust it later. And var viewport height equals 20. Let's create a sphere object. Now, how should we do this? Well, we could just write variables for the center of the sphere and another variable for the radius of the sphere, but looking ahead, we'll create scenes with more than one sphere, many of them in fact, so it makes sense to do what we did before and use classes and objects. If you need a reminder about object-oriented programming and using classes and objects, do go back and have a look at the previous video that covers that. Essentially, we define a blueprint for a sphere or anything else really, and then we make real objects out of that blueprint, and as many as we want, and that's easy. We don't have to write 10 times the code to create 10 sphere objects. So imagine we're going to do that, which means here we would create a new object. We'd say var sphere is a new object from this definition with a capital S, that class, and we'll pass it some parameters to say where we want the sphere, 0, 0 and 20 deep, and give it a size 5. Now let's actually go and define that now. So we'll say, let's define that class. So we'll say class sphere, and we have a constructor function which is called when a new object is created. Constructor, that takes the parameters, so we'll take x, y, z and a radius. And we want to give each object that information. So we say this dot sphere location is create vector x, y, z, and this dot sphere radius is r. That will give data to each object, each sphere object. So we can, when we've created these objects, they will have a location and a radius, and they could be different. Again, if you're struggling with that a little bit, I really do recommend having a look at the project and video that introduce the idea of classes and objects. It's a really powerful idea, but it's not something we're going to do again here. Great. So that is enough to create a new sphere. We'll add more to it in a second, but let's continue with our thoughts. So we've created the scene, we've got a camera location, got a viewport, we've got a sphere. Have we got a light source? Did we miss that out? No, we don't need a light source for now, because all we're doing is testing whether the rays that have come from our eyes hit the sphere or not. So at the moment we're not interested in how that sphere is lit from an external light source. So we'll do that in the next video. We're keeping it simple for now. So we want to work through every pixel in that window, that kind of viewport, which means we'll need a nested loop. And again, if you need a reminder about loops and nested loops, have a look at an earlier video. There's one specifically about that in the course. So for var, let's call it pixel x, and we are going from 0. So these are the pixels on our own canvas, the one we're used to working with, which is 800 across and 600 down. So we're saying we're going to cover all of those. So pixel x is less than 800, and pixel plus equals 1. So this will go across the canvas, and then we'll do something similar going down. We'll call that pixel y. And these will go up to 600. So actually go from 0 to 799 and 0 to 599, which is actually the correct numbering for the pixels in our canvas. So now we're visiting every pixel. Let's go and draw a picture of what we're trying to do, just to clarify our thinking. So we've got our eye, our camera, we've got this viewport, and we've got an object. And each of these things are pixels. And we're working our way through them across the canvas and down. And what we want to do is use the pixel x and pixel y values, which go across 800 and down 600. We need to convert those into coordinates, which makes sense in this 3D world we've created. So we need to scale them in some sense. So we want the middle of the canvas to be at 0, 0. We want this thing to be at, let's say, 10, 10, because the width and height were 20. This will be at minus 10, minus 10. That's that position there. So we just need to rescale them. And it takes a little bit of thinking. We've done this kind of rescaling and mapping quite a lot before. You could use the map function, you can just do some multiplications. So let's do that. We'll start typing as we're thinking. We're saying the x value is going to be the pixel x divided by 800. That'll give us a range from 0 to 1. And then if we take 0.5 from that, that'll go from minus 0.5 to 0.5. And then we're saying we multiply that by the width of the viewport width. That's it, viewport width. Phew, so that will give us the x coordinate in our 3D world. And then we need to do the same thing for the y coordinate. So that's height, pixel y over 600 and the z will always be 0. Great, so that's those three numbers there. That number, this number, and this number, x, y, z, are the positions on the viewport in coordinates that match the 3D world. Phew! So once we've got that, we need to use that to work out the, well, let's call that the current position. So yeah, let's see, var current position is create vector. Great, so that's done there. In fact, we didn't need the viewport location, did we? Because we're assuming it's at 0 when we did this. Yeah, so we don't need that. Clean that up a little bit. Just write in brackets, assumed centered at 0, 0, 0. Great. Okay, so that current position is a vector on that viewport. So now we need to calculate the ray direction. So we'll label that as current position as we scan over the pixels. Ray direction is actually just the current position. No, it's not actually, is it? So these are the vectors that point to the current pixels, and the ray is not that. The ray is from the camera location going towards those pixels. So the ray, if this pixel is at P and the camera is at C, then the ray direction is P minus C. Those two vectors subtracted. So it's P, there's a camera, so minus C goes this way, so that's C is in this direction, minus C plus P, which is that ray direction, that's the ray, equals ray. Great. It always looks complicated until you draw it out and it suddenly becomes, very simple in terms of the expressions that we write. So the ray direction, var ray direction, is the camera, is the current position minus the camera location. It's those two vectors subtracted. Now in many languages we can write that, and if you're using say Python vectors or Python kind of arrays, we could do that and get the right answer. Unfortunately, with this kind of implementation of vectors, we need to type a little bit more, unfortunately, and it's just one thing I'm not quite keen on. I guess I understand it's difficult for them to just make this work, because you have to get deep into the heart of JavaScript to do that. So we have to be more explicit. We have to say P5 vector, capital letter there, dot sub for subtracting the two, like that. So this one minus this one is done with P5 vector sub, and if we were doing adding, it would be add. So we subtracted it, but we also know that by convention, and it'll help our own calculations, the ray direction should be shrunk down to length 1, normalized. So we say ray direction dot normalize, and that'll normalize it in place, as it were. So that'll resize that to 1, length 1. Great, so we've got our ray direction. We're getting there. We've got the ray direction, which is an important vector in our calculations. Now we need to check if it intersected. Check intersection with sphere. Now, what are we doing when we do this? We want, when we check the intersection, we want we want to know if it's true or false that it did or didn't intersect. So we can create a variable hit, which could be true or false. We can do this in lots of ways, and an easy way, a logical way, is to say, well, we've got a sphere object, we should ask it to check whether a ray we give it intersects it or not. So we can make it a method of the sphere. So we can say sphere dot intersection. So that'll be a method we have to write ourselves, and we have to give it enough information for it to work it out. So we need to give it obviously the ray direction, but the direction isn't enough. We need to say where the ray starts. So camera location. That's all it needs, the camera location and the ray direction, for it to extend the ray and see if it hits it. We'll write that in a second. For now, imagine this gives us true or false, and then we can say color if intersected. So if hit is true, if hit, we can say point. Point is the command for just colouring a pixel. At pixel x, pixel y, and we can say, yeah, that's it. We don't have to colour it right now because we're not thinking about the colour of the sphere. We'll do that in the next video. Now we just need to write that method. So intersection takes, let's think out loud as we write this. It takes the ray, the camera location, and camera location and the ray direction. Those are the two things. We passed it. We can give it the same name. That's okay. And what are we calculating? We're calculating that determinant that we saw earlier, and we're returning it if it's true or false. So if we say something like delta more than or equal to 0, if this expression is true, this is just shorthand now. If this expression is true, it returns true. If it's false, it returns false. So we don't have to have separate return instructions. And now we need to calculate delta. Let's do it backwards. Determinant. So var delta was that, remember b squared minus 4ac. B squared minus 4 times a times c. Now we need to work out what those are. So let's work out A. So we'll have to go back to our working out. So A is just that d squared, which is the ray direction multiplied by itself. So let's calculate A. So var A equals p5 vector dot the dot product of the ray direction with itself. So ray direction, ray direction. That's what that kind of A is in b squared minus 4ac. That's what we worked out before. Let's work out B. We'll write the var B equals, now what's B? B is this one. It's C minus S, which is the camera location minus the sphere center multiplied, so the ray direction is multiplied with that, and then the whole thing is multiplied by 2. Phew. And you can see this would be really easy to write in a language like Python, but we have to use those p5 vector functions, which kind of adds a little bit of typing. So let's do the first bit. So there's bits to do, and then we'll say that's C minus S, and we'll kind of type as we're thinking and then fill in the code properly. So C minus S means it's p5.vector.sub and sees the camera location. And then we need this sphere, this dot sphere location. Ooh, this highlighting is telling me it can't see camera location because it's not defined here. Oh yes, it is. There it is, camera location. Ignore me, I'm getting paranoid. So that's C minus S, this thing here. Then we had to multiply it by the ray direction. So let's remind ourselves. So it's D times that. So it's ray direction times that thing, and that's going to be p5 dot vector dot dot of that whole thing. You can see it's getting quite long now, but it's not just that, is it? This thing is then multiplied by 2, so we can say 2 times. There you go. That's easy enough to do because that's outside 2 times. Finally, this C is this thing here, C minus S squared, which is this C minus S that we've done before. We can copy and paste that bit and then just square it. So we can say that's C minus S there, C equals, and we want to square that, so we say p5 dot vector dot dot, and then we just repeat that expression there. Phew. That was a lot of code, but actually we're not using b, we're using b squared, so we can say here, we can say var b squared, we're writing b2, is b times b. Hopefully this will work, because we're now using those expressions that we worked out before to work out the determinant, and only if it's 0 or more does that ray intersect with the sphere. Let's try it. Usually when I run things after having typed a lot of code, it sometimes gives an error. Could this be the time that it doesn't? Let's try it. Oh, there was an error. Let's go hunting for the error. Oh, I know, I've spotted the error. Missed out the times symbol there. So yeah, so that's one of the downsides of p5 vector for now. I hope they fix it in the future, is that it messes up the errors a little bit. So let's try that now. Whoops, still an error somewhere. That wasn't it. So I think there might be an error somewhere in here. How do we debug that? I'm just going to tidy up the code a bit because that's excessive commenting there. Okay, yep, that needs a var. That should hopefully fix it. Let's try that. Okay. That's I spotted an error. I missed out this r squared bit at the end. So the expression for that's A, that's B, and that's C, and I only did it up to here. I missed out the minus r squared. Okay, so let's do that. So that's going to be minus. I wonder if it's worth carrying on to the next line. Minus this dot sphere dot underscore radius So it's that thing squared. So that times, that's a long line, isn't it? So let's try running the code now. That's good news and bad news. It's great that we've actually got something that looks like a sphere, which means that our testing each pixel to see if it hits the sphere or not seems to be working. What we've got wrong is the aspect ratio, the squishing, because the mistake we made was our canvas is 800 by 600, but our viewport was only 20 by 20, which is a square. So we can fix that by changing the size of the viewport. What we can do is have size 40 and 30, and that shape 40 across and 30 down better matches our 800. It's the same aspect ratio, so that should get rid of that squishing. Let's try that again. Fantastic, great. We worked through a few bugs there, but it's actually important to go through that journey because when you're doing it yourself, you'll come across the same kinds of bugs. So what have we achieved? Although a black circle doesn't look that impressive, we could have drawn a black circle anyway, couldn't we? What we've actually done here is model that 3D scene with a real sphere, a camera or an eye shooting rays into the scene and testing whether those rays hit the 3D sphere or not. So we've coloured black those rays that did hit the sphere, and we've not coloured, we've left alone those rays that missed the sphere, and we've rendered a sphere. It's black at the moment. We will in the next video think more about shading it more realistically, but for now we'll pause and stop. But that's a fantastic start, even though it doesn't look like it, because we've got the core of this ray tracer already built. The core being that system of setting up a viewport, that system of casting rays into the scene, that system of checking for intersection. That's the bulk of it. Everything else is a refinement. So that's this video done. Come back for the next one, because the next one we'll start shading this sphere in accordance to how light falls on it. So that'll be a really interesting one to do, because it makes this thing look much more 3D and realistic. So we'll see you next time. Bye.